Hi everyone, my name is Vasily, and in this video we will continue talking about AiiDA Fleur. In previous video, Jens talked about the general concepts of AiiDA Fleur and also showed us an example of how AiiDA Fleur was used in a real project. And now, in this video, we are going to learn how to use AiiDA Fleur, how to prepare the inputs and analyze the outputs produced by this plugin. To do this, we will look into the structure of the plugin and understand what are the main objects that one deals with using this plugin. First of all, we'll cover the data objects, objects that usually represent outputs and outputs of a single calculation. For example, a data object represents an input.xml file, which might be a single input of a Fleur calculation. Next, we'll consider the calculation concepts, or we'll see how a single calculation process is represented in the AiiDA and how to work with them. And finally, we'll switch to the best part of the whole AiiDA code, which is the WorkChain. In my opinion, the WorkChain is the best part because it allows one to automatize the routine tasks to calculate a particular property of a material, for example, equation of states. To begin with, let's talk about the data types implemented in AiiDA. First of all, AiiDA implements the Python-like data types, for example, an integer number, a string, or a dictionary, which basically gathers all aforementioned data types for convenience. Structures are also represented in AiiDA. There's a special structure data object that helps one to deal with structures. And finally, one can work with the file data types. For example, a folder data represents a given folder, and remote data represents a folder on the computer where you performed your calculation. Single files also can be represented in AiiDA, for example, input.xml file. However, if you want to work with input.xml file, we suggest you to use a special data type which was implemented in AiiDA Fleur and is called Fleur imp data. Fleur imp data basically wraps an input.xml file and implements a lot of convenient tools to modify the Fleur imp data or extract information from it. In all of the AiiDA Fleur calculations, you will be using a Fleur imp data to submit a calculation, or you will start from a structure and we will construct Fleur imp data using the intgen calculation. We will be talking about it in detail during the tutorial. Next, let's talk about the calculation concepts and see how a single Fleur calculation or a single intgen calculation is represented in AiiDA and how to work with them. First, we need to define the concept of the code, how the code is stored in the database. Before using the code, one has to configure it following the official AiiDA documentation. We think that it's relatively straightforward. That's why we wanted to save your time and did its job for you. And you can find the pre-configured Fleur and intgen codes in the tutorial. For example, here I print out all of the relevant information about the Fleur code. We can see the reference, the name by which you can refer to this code. And this line tells us that this is the Fleur code, which defines the way how the input files will be prepared and the output file will be parsed. Finally, here we have some information on which computer the calculation should be executed and where we can find the code, in which folder we can find the code. Alright, now we have the configured code and it's time for us to think how the calculation process is defined in Fleur. There is a calcjob object implemented in AiiDA, which basically represents the fact that a single calculation was submitted, executed, and parsed. For example, it might be a single Fleur calculation or an impgen calculation. Let's have a look into the single calcjob node, which represents a single Fleur calculation. First of all, we have information in this which says us that it was indeed the Fleur calculation. Then we have the reference name. These are the PK and UUID. Next, we have an information on creation time, and most importantly, on which computer this was executed, what were the inputs, and finally, what are the outputs produced by the calculation. However, in your real life, you want to use a single Fleur calculations to perform your project, because there is a better solution for your Fleur calculations in the project. And it can help you to automatize your routine tasks or even resolve some technical problems. And it can be done by the concept of the WorkChains. And now we are going to cover this in detail. So, the WorkChain represents not a single process, but a set or a sequence of processes. But it's not so simple. You can implement a complex logic behind the WorkChain in order the WorkChain decides for you. Let's consider the example of an equation of states calculation. In this type of calculation, one wants to perform a set of calculations for different structures having different lattice constants in order to find the lattice constant which gives one the lowest energy. And this of course can be done by hand, but it's not an elegant way of doing this. In AiiDA Fleur, we have equation of states WorkChain, which accept as an input only a single structure and some of the input parameters in order to automatically calculate this dependency and determine the equilibrium lattice constant. In this way, we can treat the equation of states WorkChain as a black box, which basically performs for us all necessary calculations, and we should not worry about them. It's much easier to work with such a WorkChain rather than performing all of the scaling by hand and then gathering the results. Output of the WorkChain will be easier to understand and easy to plot. And now let's have a deeper look to the self-consistent WorkChain, which is responsible for converging the charge density. When you submit a single Fleur calculation, no one guarantees you that you will successfully converge the charge density because several problems might occur. For example, it can happen that in 24 hours only 3 iterations were done because the structure is too large. And in this case, a single Fleur calculation will just fail because your supercomputer does not allow you to perform the calculations longer than 24 hours. In case of the self-consistent WorkChain, it will understand that you had no time to perform it and will automatically submit new iterations to the supercomputer, and the problem will be resolved. So basically, the self-consistent WorkChain might be considered as a black box which accepts the structure and some configuration parameters in order to converge the charge density and calculate the total energy of a structure. First, using ImpGen calculation, it converts the structure you provided to the Fleur imp data type, which is suitable for the following Fleur calculations. Then it modifies it in a way you like, and then it checks if the calculation was converged. Apparently, when it first time enters here, it says no, because you've performed 0 iterations and it could not have been converged. Then it submits the Fleur calculations in an attempt to converge the charge density for the structure you want. And then it repeats, it enters the loop for several times until the structure is converged. So basically, after each Fleur calculation, it checks if the charge density was converged, and if not, it submits the next Fleur calculation. So, in the end, we will have the output dictionary where the total energy of the converged structure will be written to, and the folder data type where the charge density will be stored. Now, let's have a deeper look to the input configuration for the self-consistent WorkChain. As you see, the self-consistent WorkChain accepts the structure and other technical parameters as an input. Let's go through them. First of all, a self-consistent WorkChain requires some parameters that defines the logical behavior of it. We require calculation parameters that define the behavior of the ImpGen calculation. We also need the structure in order to know for which structure we want to converge the charge density. Next, we should know how many MPI processes the Fleur calculation should use and what is the queue name on the supercomputer, for example. Finally, we should define the INPGAN code and the Fleur code that will be used in the WorkChain. Now let's have a look to the self-consistent parameters that defines the logical behavior of the WorkChain. First of all, we set up the upper limit for the number of attempts to converge the structure, or the maximal amount of Fleur calculations that can be submitted within the single WorkChain. We don't really want to make an infinite number of attempts to converge a certain structure, because sometimes structure cannot be converged and no one can help it. So here we set the upper limit, and if the structure was not converged after 3 attempts, we just say it was not possible to do it. Then we define the total number of iterations within a single Fleur submission and the convergence criteria. Next, we can define the mode, or which parameter will be converged in our calculation. By default, we converge the charge density, but you can switch it to the force or the total energy. For example, if you're interested in a total energy calculation only, you can choose the energy mode. And all of the other parameters are purely technical and we won't cover them. Now, let's have a look how the output looks like. The output of the self-consistent WorkChain has important parameters, such as how the charged instance was developing during our iterations, and what is the total energy of the final converged structure, and how the total energy developed during the iterations. All of this data can be used to have nice plots that can be done using the special plot Fleur method implemented in AiiDA Fleur. And here you can just see that it looks like it was a single calculation, but in reality 3 Fleur submissions were performed, and this number is given here. This number says that this convergence was performed in 3 attempts, and each attempt apparently had 10 iterations. So that's the difference between the self-consistent WorkChain and a single Fleur submission. The self-consistent WorkChain can perform several Fleur calculations in order to achieve the result. Now let's have a look to the concept of nested WorkChains. As I mentioned earlier, self-consistent WorkChain submits several Fleur calculations in order to achieve the results. And the best thing about it, that the self-consistent WorkChain does not re-implement the same thing that was implemented in the Fleur calculations. Self-consistent WorkChain implements only the logic related to the convergence of the charge density and has no idea how the inputs for the Fleur calculations should be prepared or how to parse the output files. This is the task of the Fleur calculation. It was achieved by the use of the Fleur calculation in the self-consistent WorkChain. And this I illustrate by an arrow. So you see, if the arrow points from the self-consistent WorkChain to the Fleur calculation, it means that the Fleur calculation was directly used in the self-consistent WorkChain. In reality, there is an interlayer between the self-consistent and the Fleur calculation, and the self-consistent WorkChain does not submit the Fleur calculation directly. There is an intermediate WorkChain which is responsible for solving the technical problems that might occur when one submits the Fleur calculations. For example, it resubmits the Fleur calculation if the memory was not enough or when there were some problems with the submission. Let's have a look to the other WorkChains implemented in the AiiDA Fleur package and how they depend on each other. First of all, I already mentioned the equation of states WorkChain. This WorkChain uses a self-consistent WorkChain several times in order to converge the charge densities and calculate the total energy of all of the structures that should be calculated. Next, we have the relaxation WorkChain, which is responsible for relaxation of atomic positions. For example, using this WorkChain, one can calculate the equilibrium distance between layers in the surface. The equation of states and the relaxation WorkChain are used by the higher level workchain, the Create Magnetic Film workchain, which we will consider later. We also have Density of States workchain and other workchains that can be used for magnetic calculations that you got familiar with yesterday. These are the magnetic enzotropy energy calculation, the DMI calculation, and the spin spiral calculations. And now let's have a deeper look to the equation of states workchain and see how we utilized the nesting and the inheritance in order to simplify the logic in the inputs. First of all, in the inputs, you have a separate space for the inputs of the self-consistent workchain. These are self-consistent workchain parameters, INPCAN parameters, technical parameters such as MPI periodization, INPCAN code, and the Fleur code. These are basically the same inputs as you had for the self-consistent workchain, except the structure. As you already know, the equation of state workchain uses self-consistent workchain for different structures in order to calculate their energies, and that's why we cannot predefine them. But what we can do, we can provide the equation of state workchain with the original structure and define the rules how to obtain a set of structures starting from the original one. In the equation of state parameters, you can say how many structures we should create starting from the original one, and what would be the volume difference between all of the structures. And finally, we can define our guess where the minimum is located. And using these parameters, we can start the equation workchain and obtain the results, calculate the equilibrium lattice constant. Now, let's have a look to the other workchains, to the more complicated one, to the Create Magnetic Film workchain. This workchain uses the equation of states workchain and the relaxation workchain in order to achieve the result. And the main goal of the Create Magnetic Film workchain is to construct a fully relaxed film of a deposited magnetic layer on the substrate. For example, iron on top of platinum. And to do this, first of all, the lattice constant of the substrate has to be relaxed. And then we should relax the interlayer distance between the magnetic layer and the substrate. And as you see, we implement the logic within a single Create Magnetic workchain, which simplifies the work. And here we again utilize the nesting of the workchains, and we separate the inputs. First, we have a separate space for the equation of states sub-workchain, where we again define the self-consistent sub-workchain and the equation of states parameters. We have the same structure for the relaxed workchain subspace, where we should define the self-consistent workchain parameters and other logical parameters. And here it's very important that you are not forced to use the same code and the same input parameters for the self-consistent workchain for the equation of states and the relaxation. They are nicely separated, and it's easier to track what parameters where you use. And finally, as for any other workchains, you have a separate dictionary that controls the logical behavior of the Create Magnetic workchain. And now let's talk about the other workchains available in the AiiDA Fleur package. First of all, let's talk about the magnetic enzotropy energy workchain. Yesterday, during the tutorial, you should have calculated the energy difference for the same structure but the different spin orientations. And this is basically the magnetic enzotropy energy. In order to study the structure, one should perform a set of calculations for different spin orientations and compare and analyze the energy distribution. This of course can be done by hand using a set of Fleur calculations, but the more elegant way would be to use the magnetic enzotropy energy workchain. In AiiDA, we have two different types of magnetic enzotropy energy workchains. First of all, let's consider the self-consistent workchain. This workchain takes the structure as an input and other parameters that controls its logic, and then creates a set of structures having different spin polarization and submits a self-consistent workchain for each of them. After some number of iterations, usually it's around 50 or 60, for each of the structure, the data is gathered and the output is created. Next, we have the force theorem version of the magnetic enzotropy energy workchain. It accepts a structure and other parameters too, but in contrast to the self-consistent version, it first converges the charge density for a single structure and then uses this data to perform a single iteration magnetic enzotropy energy estimation. And in this case, we end up with a less accurate calculation of the magnetic enzotropy energy, but which takes much less number of iterations that might save you the computational time and the resources. And as always, after the submission of several calculations, the data is gathered and the output dictionary is produced, which is very easy to analyze. Another example of the workchain is a spin spiral dispersion workchain, which basically calculates the energy difference between different spin distributions. So there's a spin spiral structure which is defined by a single number q, and basically what we want to know how the energy depends on this vector. And again, similar to the magnetic enzotropy energy workchain, we can calculate it in two ways. First of all, we can converge the charge density for all of the structures that we want to calculate, or we can perform the force theorem calculations that can save us the computational power. Let's have a look to how the self-consistent version of the workchain works. The concept is basically the same as it was in the magnetic enzotropy energy workchain. First of all, the workchain takes a structure and the workchain parameters that controls its logic, and then sets up the self-consistent calculations for each of the structures. It takes about 50 to 60 iterations for each of them, then data is gathered and the output is produced. And in order to save the computational power, one can use less accurate but faster way of doing this, which again takes the same structure as the input, has quite similar input parameters, then performs the reference calculation in order to get the charge density for a reference, and using this reference performs a single iteration for each of the structures in order to estimate the energy. In the end, the data is gathered in a convenient way to analyze. At the end of my talk, I'd like to acknowledge the Fleur development team and my colleagues from the Virtual Materials Design team, AiiDA developers and our IT department. I would also like to thank my colleagues who took part in the tutorial development and our funding agencies. So let's summarize my talk. So today we've looked how one works with inputs and outputs in AiiDA, how they are represented, and for example, input.xml file is represented by a Fleur input data object, which is easy to work with, which implements certain methods to modify the input file or extract the relevant data from it. We also had several examples on how the dictionaries were used for the WorkChain submissions, how they controlled their behavior. In the middle layer, we have covered the Fleur calculations that are represented by calcjob objects. And for the Fleur calculation, we had a specific object which is called Fleur calculation, which deals with a single Fleur submission. We also covered how codes are represented, what information is relevant about the codes and how to use them. And finally, we have looked at the WorkChain concept, which are ready-to-use key-turn solutions for a specific problem. We covered almost all of the WorkChains that are available in the AiiDA Fleur plugin: equation of states, magnetic enzotropy energy, and other WorkChains. This is the end of my presentation, and I hope that you enjoyed watching it. Now I will be waiting for you in the tutorial room, and I hope that you will get the deeper knowledge and look on the practice how things work in AiiDA Fleur. Thank you for your time.